Okay, let me get started. Let me know if you cannot hear me clearly. Let me uh, see how I put the mic. So can you hear clearly? So you may come.
Yes.
Oh, thanks. So okay, let me do a little bit recap and let me turn off the. Let me turn off the volume on the other side. So I'll do a little bit recap. And so basically, I guess we introduced several information measures like the entropy, like the, say, conditional entropy, and then a mutual information, and maybe a conditional mutual information. So so if you don't get familiar with them, like it's okay because I will look, I mean, kind of like continue to repeat a little bit about like each of them. I guess to start with, like for the entropy itself, I guess, of course, the entropy, say, the unconditional one is the, you can think of that as the amount of information per sample, or actually I should say average amount of information per sample from a discrete memoryless source, where the discrete memoryless source have a probability distribution Px. And so of course, you know, this is just equal to expectation minus log Px, right? So also like be careful, like here, I try to always try to be careful, like maybe sometimes I'm miswritten or like I've typo, but like when you have expectation, like this should be like a uppercase letter, because this is supposed to be a random variable. Right? If this is like not a random variable, for example, if I write something like that, so it means that it's for a particular instance of x. So you like sample the source like with x, then this is just a constant. Actually, this will be just equal to itself. Yeah, but on the other hand, when I write like this, it's actually, as you know, this should mean something like that, right? Px minus log Px, right? And now I guess I didn't emphasize that earlier, but probably you have already realized that, like, this is another way you look at this expression is it's very intuitive. Is you can think of this as like a weighted sum of like for all possible outcome of x, and whenever you pull an outcome of from the source, let's say after this discrete memoryless source, this discrete memoryless source like Px here, whenever a sample from this source, that sample, like if I get a sample x, you can think of like for that sample x, the amount of information for that particular sample will have like information minus log p small x here. So therefore, like this expression is really a weighted sum of them. So even though sometimes I kind of like a little bit sloppy when I say like this is the amount of information, but always think of like this is actually the average amount of information. So when you pull out from this source here, each time the amount of information can be different. Let me give a very concrete example. Let's say like if you think of the source is just like source for like English letter. So let's say like for each of the character, you have a paragraph or you have a sentence, and this DMS here trying to model like English language for each of the character. So as you know, like for some of the character will have more information, some of them may be less information. So for example, like for character E, like you know it has actually, and also you see that like the more probable like outcome will have like less amount of information. So therefore, like E being the most common character, it actually has the least amount of information. So, and if you have something like a Z, probably has much more information there. For example, like if I have ZO, something like, I more or less can guess like this is related to animal, right? So, but for example, if I have, say, E, for example, I see took or poke or something like that, this E here doesn't give much more information here, right? So if you already see the earlier letters, say TOK, POK, or something like that, like this E here, like actually doesn't help too much. On the other hand, if you think of this T and P here, they are much more informative, right? Because if I remove this letter here, you don't know like what's the actual word there. Basically, that's not you can guess the actual. Of course, you can from other letters like get the context or something. But here, I just want to emphasize like the amount of information for each of the outcome is different, and it will be. But the more probable outcome will have less amount of information. On the other hand, the less probable outcome will have more information there. So then, like you basically just do the weighted sum. That is totally, reasonable. If you think of that way, like I think this, the definition of HS become very obvious. Of course, we also show that why we define like this using the law of large number, and basically like, yeah, I won't repeat that part. So any question here? I just want to, because I think I didn't really emphasize like the expression here. Like you can just look at this expression and oh yeah, it makes sense, right? So of course that is the average amount of information. So and also like, oh, actually, by the way, then I think we mentioned the upper and lower bound for that, right? So for the entropy itself, of course, like the amount of information is always bigger than equal to 0. But of course, I keep on emphasizing that is that this is only true for continuous, for discrete source. So if I'm considering like a continuous source, okay, you will see that like, okay, anyway, maybe later on, like I will more, of course, we already mentioned that, but we didn't actually explicitly cover that. But for discrete, for continuous source, we will have the definition will have like integral instead of like the summation. And in that case, this is called the differential entropy, and that differential entropy can take negative values. And so, but for the discrete source here, hx can only be positive. And of course, we also know that like hx is bounded by log the size of the alphabet, right? So if I use the unit bits here, then it will be log base 2 here. Yes, actually, by the way, like maybe just it's not common, but like just something like you may come across, but very unlikely, except you read very old paper. There's also a unit for information using so-called nets. So nets is like when you take, instead of take a log base 2, you take lateral log here. So you have a unit net instead. So of course, like the difference here, like taking like log base 2 or lateral log is just like a different from a constant, right? Because you have log 2x is equal to, let's say, or like, doesn't necessarily x, maybe log 2a is just equal to log lateral log a over lateral log 2, right? So therefore, like they only differ from a constant. So therefore, like it's really the difference is like just a unit. So therefore, so when you say like, yes,
yes, I had a question. Yes.
Yes.
The question is, when you said that h of x is bounded by log 2 base x, what is that x?
Yes, x is the alphabet size here. So x is the alphabet. So yeah, I probably should.
Alphabet size, you mean by in terms of bits, or like I'm a little bit confused about that.
So for example, like if your source here is just binary, then your this alphabet here is we just 0 and 1. And if you have a dice, then this alphabet will be like, let's say 1, 2, 3, 4, 5, 6, right? So this thing here is just the size of this set here, or like a more formal word would be the cardinality of this set here. So for example, in this case, for binary case, this will be just equal to 2. And for this number of dice, it will be just equal to 6, right? So
number of possible outcomes, something like that.
Yes, so this is a set. So you think of this as a set. This is a simple, just denotes like the size of the set. That's number of elements of the set.
Okay.
So sometimes you see also like people call it cardinality or something like that, but you can just think of it as the size. So if you have like 10 outcomes, then the size will be 10. Is that clear? So so then if you look at this expression, it's very obvious, right? So for example, you think of think of like yeah, binary. Of course, binary will be just if you just have 2 outcomes, 0 and 1, you just need 1 bit to store that way. And if I have 4 outcomes there, 1, 2, 3, 4, then I will need 2 bits to store that 1, 2, 3, 4 different values, right? And so in general, if you have like n outcomes, you just need log 2 n so many bits to store that. And you will never need more than that, right? Because like each time you from this source is basically some, for example, let's say I have 4 outcomes here. I can 1, 2, 3, 4, and each of them, right? I can just code each of them say 1, 2, 3, 4 as a 0, 0, 0, 1, 1, 0, and 1, 1, let's say, right? So then like each time, it's like maybe I rewrite here. So let's say if I have like this x here can take values 0, 1, 2, and 0, 1, wait. 1, 2, 3, 4, just say 1, 2, 3, 4. And then like, so what is compression? Or like, think of this as like some coding scheme here. I have like an encoder. My encoder is just like convert this into bits, right? So I can convert this into, let's say, whenever I see a 1, I output 0, 0. I see a 2, I output 0, 1, and output 3. If I get a 3, I output 1, 0. If I see a 4, I output 1, 1. So I would just need 2 bits for that, right? Regardless, like I don't care about the distribution here. So for example, if this distribution is super skewed, in the sense that I always just get 1, then of course this is silly, right? Because I always get 1, there's actually no information coming in. I can have this encoder, let's say I have another decoder here. My code here, of course, is like after I compress this source, let's say I got this compressed source here, I want to recover that. Then let's say if I use this coding scheme, like if I see a 1, I relabel is as 0, 0, 2 as 0, 1, and so on. Then for the decoder, we just map it back, right? So for example, like if I have this streams coming out is really 1, 2, 3, 4, right? 1, 2, 3, 4. Then my output will be basically get a stream like 0, 0, 0, 1, 1, 0, and 1, 1, let's say. Now, seeing this thing here, then the decoder will just recover, okay, I read 0, 0, therefore I get back 1, I get 0, 1, I get back 2, and so on, like 3, 4, I output that. What I'm saying, like this will work no matter what kind of distribution it is. As far as like the alphabet size is x here, I can always compress this source into log 2x, so many of them, right? But what I'm saying, this is not optimum when the source here is skewed. So in the sense, it's not uniform. because in the extreme case, as just I mentioned a moment ago, that if like my source is so skewed that it's always giving me one, always just send out one, then this is meaningless. I keep sending 0, right? Because my decoder and encoder already knows that like this guys here is always output one. I should do nothing. Basically, I don't need to send anything. My decoder is always just like send 1. Or like my encoder can be just counting like how many ones that is receiving, then tell the decoder, okay, I received 5 ones. Now I should just send 5. So then in that case, you don't need like for example, if I have n samples here, like if I do these stupid things, I will need 2 MBs here to compress this source, right? But if I know it's all sending 1 anyway, then I will just need a number that would be like, that number will need log n, let's say, or anyway, like you think of a number, say maybe 100 bit, maybe just a double, like maybe 64 bits, right? No matter how long is this. So of course, you cannot represent more than like 2 to 64 anyway. But what I mean is that you will need like much less number of bits to send out that to compress this source here. Then this is two extreme case, right? This is like when it's your total uniform. This is a total skew, but in general will be a mix, right? In general will be like sometimes some of them will be more likely to happen. For example, maybe I have more 1, but I have less 4 here. Then in that case, I maybe. No, by the way, let me know if you have any question. I guess I am digressing from what I want to talk about, but since you asked, maybe it's okay. Like, do you guys know Huffman coding? So Huffman coding, like, it's just a okay, it's like a technique, something like zip. So everyone knows zip, right? Or WinZip, or like anything, like it's trying to compress a file and so on. So this is just a method like to compress. So by the way, this is an interesting story about Huffman coding. If I remember correctly, like of course, Huffman is very smart. Like he is a master student or something at MIT and so on. Like then one day, I guess the professor there is probably Fano, but I'm not 100% sure. And he just gave a assignment to student. Like he doesn't. I mean, Fano himself didn't know a solution, but he said like, okay, give him a discrete memory source. Let's devise the optimum algorithm to compress the source and give it as a homework assignment for 2 weeks or something like that. And then Huffman just come out with a solution, and then that become a paper. So it's like very famous Huffman coding. But the idea is very simple. Like, so let's say if I have like this source here, let me make a little bit more outcomes, more than 4. Maybe 4 is too simple. Oh, maybe 4 is okay. So I have like 4 values here. And let's say the probability of these 4 values is 0.1, 0.1, and then this 0.5. That may be too simple, honestly. And this is like 0.3. So what Huffman coding does is like, it want to design a code word, a compression, or like I should say, a compression scheme for this incoming source here. So like what I did here, like whenever you see a 1, I'm output a code word here, right? Let's say 1101, 1001, and so on, right? When okay, or I should say like whenever I get a 1, I output 00. I got a 2, I output 01, and so on and so forth, right? As I said earlier. But this is not a optimum way to do things when your source is not uniform. So for example, for this source here, intuitively, as you see like more free than the west here, so probably you want to do is like you want to have a code word that for free is shorter and for one is longer, right? So no that like I cannot, but there's a limitation here, like in designing the short code. For example, like I cannot have code like something 1001 and 10. So by the way, like, okay, maybe this is an exercise question one. Why this is bad? So am I clear here what I'm doing here? Yes, okay. You guys are very quick. So yeah, that's I think it should be question 0.1 or something, but the other guys say get it. So it's there's a limitation. Like no, it doesn't need to be the same name. Yes, that's ambiguous, but it doesn't need to be same name. For example, like I can do something rather stupid. For example, like I do here, I can have like let's see, 111 1001 and 00. I think it will work okay. So even though like it, yeah, I think this will work. So okay, of course, like this code is very stupid, right? Because it's basically the same as this one, but here I pack one more here. Maybe I do even something like that, right? So I can have a code like when I have receive a 4, I say output 00, receive a 3, I output 01, and output. You I don't quite get your, unless I don't quite get your comment actually. So do you mean that like you don't know where it ends, like when the length is different? Yes, okay, but in this case, it's not ambiguous actually. If you write it out, for example, like for one thing, like of course it's kind of silly. When you have at least for this example, it's totally fine, right? If you look at that here, the only chance you have 4 ones at the same time, it has to be this thing, right? There's no way you can do something other than that, because you have like 01, 10, like for example, you can have first you got a 2 and then a 3, you get like 01, 10, but you only get 2 1 here, right? There's no way you can pack into 4 ones here, and therefore like, there would be low ambiguity here actually. Of course, it's a little bit hard to see all these possible combination for that. One way that I didn't, okay, I drag into the contents that I didn't expect to cover, like this year that I said I won't cover, but I guess I just cover a little bit. It's like there's something like long as prefix-free code. I guess it's okay. Like just get a little better intuition or something like that. So the idea is very simple. It's like if I have each of the code is not prefix of the others, then I can for sure that even the length is different, then you can uniquely, unambiguously recover the source. So for example, like if I have like 0 and then 1, and then, okay, 0 and 1 probably is not good. Then I cannot do anything else. Maybe 0, 1, and then 0, okay, 0 is not good. And then yes, 1, 1, 0. Okay, let's see a code like this. I'll claim like this one. If I have a code like this, this is, I can uniquely recover the so-called like uniquely decodable, uniquely decodable. So if I have like the code, for example, this is again a 1, 2, 3, 4, have a code like that, I will be always able to recover the source, like no matter what kind of combinations for that. So because my argument is that if you look at each of this code here, so you don't have any of this code word, like for example, this code word, compare one code word with the other code word. You don't have the code word, one code word is contain the other code word as prefix. For example, like I don't have like, for example, if I have an extra code word 1, 1 here, let's say, if I always say, well, I have a 5 and I have a code word 1, 1 here, then this guy and this guy will come out with problem, right? Because at this time I'm reading, like for example, like I'm reading the stream here, like 1, 1, something coming in, and then I'm not sure like whether I should end here. Like is that 1, 1 is referring to this 5, or like I have something else here, like 1, 1, 0 is referring to 2 here. So at least like I cannot immediately recover like that. That's I cannot oh, that's I made up more names here, like but this is like the formal names we will really call that. This is like instantaneous code. How to spell instantaneous? I'm thinking it's about like this. So instantaneous meaning that like you cannot read, you don't need to read ahead to decide whether this is the right code word or not. So for example, let's see. Oh, okay, I don't track into that. Like I guess but let's just focus on instantaneous code. I don't think I need to go so far into that one. So one claiming that if I have the prefix-free code, basically each of the code word does not contain another code word as its prefix, then it always will be instantaneous. So you agree with that, right? So for example, if I don't have this guy here, then I continue to read, right? So if I have some, so I guess let's say this is like the streams coming this way. So I have like 0. When I see 0, I can stop here, right? Because there's no one else, there's no confusion here. Like any other code words will have 0 here. And let's say if I have 1 0 here, when I read and then I read 1 0, then I can also stop here. I know this is like decode at 3, right? Because no other guys will contain 1 0 as prefix. So there's no ambiguity here. And then if I have 1 1 0 here, again, I don't read 1 1 and then 0 here, I can stop here, right? Because I know no other guys have 1 1 0 besides this code 2 here, or this input 2 here. So this I can output 4, 2, 3, and so on. Yes, actually, that we can go back to the Huffman coding. Maybe I just go back to Huffman coding. So yes, you probably need to redesign the when you have a new yeah. I guess let me just do a very quick example for this guy. I don't think like I should spend too much time on that. So for Huffman code, like the idea is very simple. So as you can see, like because like apparently if you have source here, if you have something is less likely to happen, you want to make it make the code word longer, right? If like you have an outcome, like you have you have like a character, let's say like it's less likely to happen, you can afford to have a longer code word. So therefore, like Huffman is doing something like that. So it will basically merge the, get the smallest two probability among all the outcomes here. Like let's say this two is like the minimum, then you just combine them together. So then you go together. Now you think of this as like only one element now. So I group together and also I will add the probability. So I have 0.2 here. Now I consider this as a new one element here. And then I look at this other, compare this one and the rest here. And again, I pick the two that is smallest, then I group them together. So I have this new probability will be 0.5 here. And then finally, like I have these two grouped together, right? Yeah, and I get, something like that. So then when you create the code word, you're just going back, like, for example, like you can go to upper vowel would be 0 and then lower vowel is 1. Then you have code word for, let's say 3 will be just, I will code word, have a code word 1 here, and 4 will be like 0, 1, and 2 will be like 0, 0, 1, and then like 1 will be 0, 0, 0, something like that. And you also like this kind of construction, like you will have the code word length will be approximately equal to log px. And that's exactly what you want, because like, you know the amount of information, like from earlier, you know the amount of information actually log px there. So therefore you want to match this with log px, right? Because you want to have the number of bits to store that particular particular input element is the same as the amount of information it has. Yeah. So okay. Anyway, I don't even know why I'm talking about this. Yes. So okay. I actually I want to ask you guys, but I think you know already. So when do I have like when I have the upper bound, when do I have hx is equal to log 2x? So it is, I guess it's apparent now, like after all the discussion here. When does that happen? Maybe I should still make it the question. That's okay. When do I have like, so I said like this as an upper bound and lower bound, right? So I have hx here is lower bounded by, I'm sorry, like I'm not too organized. I think I've written somewhere here, but like now it's okay. Like, yeah, it's upper bound by this way and lower bounded by 0, right? So when do we have the upper bound happen? Oh, okay. Let me repeat again. So let me backtrack a little bit. So okay, maybe I digress too much that therefore like some of you guys get lost. So so let's go back to the information theory. Like this is a more like compression. Like this is a still information theory, like for Huffman coding and so on. But those are not our main focus. But I'm saying our focus is more like think more high level, like what's the information there and so on. So remember that like okay, we can think of like hx represent what they say. Hx is like hx is like the number, not number, I should say the amount of the hx. So when you have a discrete memory source here with like distribution px here, you can think of per sample, like when it's coming out from this source here, Okay, now actually, like maybe I recap a little bit what we have, like why we come up with that. So if you take a long sequence of that, like x1, x2, and so on, like up to xn here, then we say by law of large number, like all this sequence will have the same probability, and if the probability is equal to 2 to minus n hx. And also, like consequently, the number of like typical sequences will be just equal to 2 to n hx. So basically, if you pull out a long sequence from this source, each of these sequence will be will all have the same probability, and also like all the possible sequences you can count them will be just equal to 2 to n hx. So therefore, like of course, if you want to label like 2 to n hx sequences, you just need n hx bits, right? So therefore, like the number of bits per sample is just equal to hx. Then we claim that, okay, for this discrete memory source, the amount of information from this source on average per sample will be just equal to hx bits, right? And then we show that, okay, like this hx is upper bounded by like log x. Here, x is the alphabet size, or like the absolute x is the alphabet size. So it's basically the number of possible outcomes. So what I'm saying, like, when will this happen? Like, when will this happen to be, oh, okay. When will the equality will happen? Basically, like, hx is equal to log 2x. Yeah, okay. Yes, that's exactly the case, right? So when, even though we don't have a proof here, but of course you can prove it yourself, but what I'm saying, like, actually, yeah, you can show it very easily, right? So when all of them are uniform, yes, then you can just, when all of them are uniform, let's say, then px will be just equal to 1 over x, right? So the number of outcome, yes. So therefore, like this will be hx will be just equal to x 1 over x log 1 over x, right? I have a minus sign somewhere here. So then will be like equal to, and this is like basically, yeah, I can pull this out. This is just a constant, right? So I equal to log x here, right? And then I can sum over 1 over x, that is just equal to 1, right? So therefore it's just equal to log x. Yes. So okay. So now let's continue with the conditional entropy. Let's.
Dr. Chang?
Yes.
Yeah, I've got a question here that
Yes.
if the sequences that you made, I guess 000 was for 1 and 001 was for 2, and then only 1 was for 3 and 01 was for 4. But in that case, we still have the ambiguity if we only have say 1 or 1 0, still we are not really sure which sequence it is referring to, because the number is in fact 1 in all the 3 cases.
Oh, are you talking about the coding things like earlier, or like
the Huffman coding that I guess you generated?
Oh, okay, the Huffman coding, yeah. So let me, if I remember, what do we have, like it's like that, I guess. I forgot. Yeah. So yes, we have 1 2 3 4 here. So we merge this way, and then merge this, and then merge this. Yes. So I got like, I think I put the code word is something like that. So I have like 4 will map to 1, 3 will map to 0 1, and this will map to 0 0 1, and this will map to 0 0 0. Yes.
But in that case, the last 3 words 0 0 1 0 1 and 1, they are representing the same value. So will there be any?
Okay. You need to have the entire one is a prefix of that. So this one, you consider not just this is in common, but you consider like whether this is prefix from this guy here. Because if you, for example, if I code something like 432, then I have 1 and 0, 1 and then 0, 0, 1. Now, if I add the decoder sign, so I look at 1 here. So this is only match, right? I don't have any other match. And I read 0, 1, 0. I don't have anything though. I keep read on, right? So it can be this one, and this one at this moment, right? But when I read 1 here, I can only have this guy, right? Because the rest of this guy is not prefix of this one. Yeah, there's no ambiguity here. So I can move on. I know, okay, this should output 3 here. And
Okay.
similarly here, if for this one I read 0, I don't know which one yet at this moment. It can be this here, right? So, but then if I read 0 again, I still don't know which one. It can be this one and this one. But then when I read 1 here, now I'm done. Yeah, it has to be this one, right? So,
Okay.
so there's no ambiguity here.
Sure,
Yeah.
thanks.
Yeah.
Dr. Chen, I had a question.
Yes.
So the last question was, when does the condition that is shown in the red box
Yeah.
that holds?
Oh, no. I'm sorry, like here.
When h of x equals to log 2 base x.
I want to write it, but I guess for a short instance, I point to here. The second question I want to say when the upper bound will be satisfied as an equality. So basically, like when does hx reach this one?
Right.
Yeah.
Because when it's equality, then the answer is correct. What everyone is saying, like same probability for each symbol, but this holds always, right?
Yes. This one holds always. You always have like bigger than equal to 0 and also less than equal to this guy.
Got it. Thank you.
Yeah. So let's see. And yes, I like to talk about a little bit more. I actually, it's also partial recap also. I guess this is good, right? Because I know all this is pretty new for you guys. So but it's actually pretty simple, but because it's you probably not see that maybe you saw it once or twice sometimes in paper, but you never really went through any of this, so it may be pretty foreign for you guys. So I guess it's okay to repeat sometimes. So now for conditional entropy here, I just realized I never really motivate that. Like and then I look through my notes. I thought like in the past I motivated that, but I didn't. Then I gave some thought like it's actually I can use the same argument to argue that like hx given y is basically the amount of information left for x given that y is known. So I can use a very similar setup that like we argue with like hx, like when we argue like how we argue when we argue how we ended up with hx. So let's say if I have a joint source here, x and y, pxy. Now again, it's like a discrete memoryless source here. So, but now instead, like we spit out like a couple like x and y at the same time, let's say. So each time you got a pair like x, y, kind of coming out from this source, like you have like x1, y1, and then like next instant you have x2, y2, and so on. And this pxy is constant. So basically, like for each time instance, this distribution are the same, and it's discrete also, like x and y are discrete, and so therefore it's a discrete memoryless source here. Now for this one, I can do a very similar setup as we have earlier. So let's see like if we try to compress this x here, so I'm trying to encode this x into something, right? And but this time I will have some help from this y here as a side information, or like as some helper information that we put into the encoder as well. So then let's say I compress into some code word C here, and then I decode that, let's say, and then I want to recover back this x here. And again, I can take a sequence of that. Let's say I take a sequence of X, a sequence of Y, and then I compress, I take in a sequence of X, a sequence of Y, then compress into a number or like a very large number, a code. And then I recover that back also with this help of this side information. And let's say I get back this X hat N. I want this X hat will be the same as X N here. So that's what I want. Now, what we can think of is like, maybe I take a simple, yeah, it's okay. Let's say I consider Y can take different values, right? Maybe, okay, let me really start with something really simple. Let's say Y can take value just 0 or 1, let's say. So if Y can take only 0 or 1, what I can do is say, for my sequence coming in, let's say I have X1, X2, maybe I draw and put right in this direction, X1, X2, X3, and so on, like, let's say Xn, right? And some of them will have Y is equal to 0, and some of them will have Y equal to 1, right? Maybe I have this X4 is 1, X5 is 0, let's say, something like that. Now, what I can do is say, I can group at the encoder, I can group together, like, for all the X that have like Y is equal to 0, and all the X with Y equal to 1, like as 2 groups, right? And now, so let me ask you, like, okay, maybe let me ask you, like, per sample for group 0, how much bits, or maybe I shouldn't say per sample, or like for group 0, like, for group 0, basically, meaning that Y equal to 0, how many bits per sample are needed to my handwriting, to compress basically the source, compress X. Is that clear what I'm doing here? So even though like this discrete mammillary sources are spitting out X and Y at the same time, but we only care about X, we don't care about Y, but we take Y as some helper information to compress X. And what I'm doing here is basically, I'm going to kind of separate into 2 different group here, right? So I consider, okay, sometimes I use, for the case like when Y equal to 0, I will group all the X together. So in the sense that in that case, basically this will go to Y equal to 0. I have something like X1, X2, and then I will have X5, right? And blah, 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 something like that. And this, I have another group is like Y equal to 1. I will have like X3, X4, and something like Xn, something like this. Now, what I'm asking is like, for this stream here, so if I'm going to compress it, so I guess I'm trying to guide you guys to think along the line exactly what we did, like when we do the when we did the same argument for the unconditional entropy, just Hx. So essentially, we can do exactly the same thing here, right? So instead of we have the distribution is Px, right? At this case here. Now I have a different distribution for this guy here, right? But it's the same because for a given Y here, so each of these samples here have the same distribution also, right? Not exactly. So it has something like if they are completely correlated. So if you have x and y are kind of like completely correlated, let's say x equal to y, something like that, then it will be as yes, actually it's very close, but you're jumping a step ahead already. So how about like for y equal to 0? Just for this, so I have two groups here, right? It doesn't have to be n over 2. So maybe some of them will go to maybe this have n over, but it's not n over 2, right? Actually, this will be something like py equal to 0. I think you're thinking something like if py equal to 0 is equal to 1/2 and py equal to 1 is 1/2. But let's say like in general, this doesn't need to be 1/2 and 1/2. Conditionally actually has the closest answer. Yes, precisely, right? Because like now what we have here, you think of that like this is exactly the same argument as before, right? So we have that if your source is px here, when the source coming in, we say like we count the typical sequences there. You basically like the number of typical sequences, if you have length n here, the number of typical sequences there will be 2 to n matrix, right? I can label all of them like basically will be with like n matrix bits therefore, right? Therefore per sample will be hx bit per sample. Now in this case, it's like you think of if I have this pxy coming in, but I split them, right? I split them, I only take one is like px if y equal to 0. So or like maybe I should write like I have a stream here like x1 up to something like that. But I split them like some of them this is like x as I have like x1, x2, x5 and so on and so forth. And the length of this guy here, of course I split them like will be shorter than n here, right? Will be approximately I have like n p y equal to 0. So many samples here, right? And then like for these samples, like all the samples here will have distribution like px given y equal to 0, right? Or yeah, maybe I should write big y here. Px equal to y equal to 0 here. And then, so therefore the number of typical sequences here will be like 2 to the npy equal to 0 times h x given y equal to 0. And therefore you will need like npy equal to 0, hxy equal to 0 bits here. So because you have npy equal to 0 so many samples, therefore per samples will be x given y equal to 0 bits, right? Now, of course, by the exactly same argument, for the other side here, I will need like hx given y equal to 1 number of bits there. Now then the total, I mean average number of bits per sample needed will be simply the weighted sum, right? So because I have like approximately py equal to 1 that will have y is equal to 1 and py equal to 0 or like I should multiply by n. I have like n, yeah, anyway, I have the fraction is like py equal to 1, so many of them will have y equal to 1 and py equal to 0, so many of the fraction of them with py equal to 0. So I should just weigh the sum of them. So therefore, like the average number of bits at the end here, average number of bits to store this C here will be just the weighted sum hx given y equal to 0 times p y equal to 0 plus hx y equal to 1 py equal to 1, right? So in general, like so therefore in general, the number of bits needed is just like x given y equal to some small y probability of y, right? And my sum over y, right? So this is exactly the definition of hx given y. So therefore, like hx given y is really when you have a setup like this, you can think of like if I given you this side information, like some help of information, additional information y, and if I know y, I want to know like what's the remaining information I need to compress the x. So you can think of what's the remaining information of x given y. That would be like hx given y. Of course, it's all of this is per sample. Like for each of the sample on average, if you know y, what's the remaining information of x. So then like I hope this motivate better like that I omitted last time for this. So so then like the mutual information, therefore like the definition is quite reasonable. So we have the mutual information is hx minus hx given y, right? Okay, let me check. I have a list that like, I want to cover. Let's see what stuff I just make sure I didn't miss anything. I covered that. Yeah, okay. So so this is very reasonable then. If you think of what's mutual information, it's like saying, okay, if I have x here, the amount of information of x is hx, and then like knowing y, the amount of information left behind is hx given y, then ixy will be just meaning the amount of information shared by x and y. So that's what we mean by mutual information. And then also immediately we can easily argue, for example, like from this setup here, is that like hx will be bigger than equal to hx given y, right? Do you agree with that? Because like knowing something, of course, the remaining information should be always smaller, right? So if you think of like, I'm going to compress this source here, I can ignore using this guy, right? If I don't use this side information here, I'll just get back hx. But if I use this side information, of course I will gain, right? There's no way I will lose. So therefore, I will always have like hx given y is less than hx here. So this sometimes people call it like conditioning reduces entropy. So we will show it like more vigorously later on. Just write down the algebra and so on. But I will kind of delay that like later today. But intuitively, just look at what are they and the argument from this setup. Apparently, this has to hold true, right? So therefore, like we always also have, because ixy is equal to hx minus hx given y. So therefore, this is also the mutual information has to be always larger than equal to 0. And also, like, I'm jumping ahead, like, as a remark here, for continuous random variable, like, we have this differential entropy. So therefore, like, we can also define like mutual information as something like that, even for continuous random variable like h. This differential entropy will have like integral instead of summation. I can have like ixy is equal to hx minus hx given y. And unlike the case like for entropy and conditional entropy, that like for differential entropy, you can have like you can have like negative values for differential entropy. For the mutual information, like for variables here, regardless they are discrete or continuous, this mutual information, it turns out, is always bigger than equal to 0. But yeah, but we'll show that also like later on. Yeah, but it's good to mention it here, guys. So that's the, I guess like it's also clearer here now. So let's see what else I want to cover. And okay, maybe just a simple exercise again. Just check your. I don't even know what's this question number. What it's 4 or something? I don't know. I got really. I lost track of the number. So or 3. I don't know. Anyone know? I think it's 4. Okay. So let's say what's x plus 1 given x? So let's say x a random variable, right? X plus 1 can be a random variable as well, right? Was hx given plus 1 given x? Yeah. So knowing, yes, when you, so in general, so therefore remember that actually in general, if I have h, I have some fx here. If f is a deterministic function, so this is always equal to 0. So if you know some x here, if then fx you know for sure, right? If this is deterministic, then this will be just equal to 0. So this, so therefore you can have a constant here, you can have whatever, you can have like multiplied by something, all of them will be equal to 0. Let me, okay. Yes, I guess okay, like hxy, of course I know hxy, maybe I rewrite hxy again. Like hxy, as we said, like this is equal to py is basically hx given y, something like that, or y, right? And I have hx given y is equal to this expectation of minus log p x given y, right? And this would be just equal to y x p y p x given y minus log p x given y. So this is pxy. I have some xy here. And then I write like minus p x given y. So I expand all this into summation form. Just want to kind of make sure because when I first studied that, like sometimes I kind of made mistakes like this. Like here, when I write down summation form, like everything becomes clear, right? The expectation form is very convenient, but sometimes it's not exactly completely sure. For example, if I have log px given y here, so know that like in this context, of course I can write this conditional entropy as like something like that. But whenever people write expectation, like you're assuming it's taking expectation for some distribution, but the distribution is not exactly specified here. So you need to be careful like what kind of distribution we're considering. So in this case, like for example, like maybe, for example, like for this one, if I have like px small y log expectation, this guy here, so when I write like this, it's not actually completely sure, like, am I doing expectation like over the conditional distribution, something like log p x given y, sum over x here, or I'm just expecting over the marginalized distribution, like px log p x given y. So in this case, we are really like wants to have this one, but I guess when we write like this, you need to be very careful, like which one we are. So when you're not sure, like I guess it's always sometimes it's just expand everything into this summation form, then like everything is clear. But whenever the context is clear, then like I guess writing this expectation form is very convenient. So therefore, like I will still like use it quite often. Also, like it's more easy to read and like more intuitive. But yeah, I need this like summation form here. Sometimes in particular, for example, like let's say I want to verify whether like ixy is equal to iyx, let's say. So from this definition here, it's not clear this is symmetric, right? Because I say ixy is equal to hx minus hx given y. So how do I know that hx minus hx given y is actually equal to hy minus hy given x? Okay. So in that case, the best approach would be just go back to the I would say the elaborated form, like with the summations. So let me verify this one. So I mean, I want to see like if these two are actually the same. So let's look at like what's ix, or like what's ixy, by the way, in the summation form. So I have, as I said, like I have hx given y is really just pxy log px given y, right? I have a minus sign here, let's say. And I have like hx is equal to sum over x px, right? Log px. Again, I need the summation form. I mean, minus sign here. So then if I have like hx minus hx given y, then would be equal to this guy minus this guy, right? So I have like x y. Okay, what I'm going to do here is I want to have also something like px. I want to write it in pxy form. How do we do that? So if I can write like this thing as like pxy as well, then this multiplied by this guy only have this thing here, right? Subtract these two guys. Yeah. So it's not exactly like conditioning, but it's like marginalizing. So marginalize is like if you have like a joint distribution, if you, or like I should say like a inverse marginalize. So if I sum over one variable, then we will just get back the remaining variable, something like that. So therefore I can write px as the summation of like pxy, right, with summation of y here. So therefore like I have this guy, I can rewrite as a sum over y pxy, right, and log px here. So I need a minus sign here, then this minus I have plus here, right, xy p xy log px given y, right? So, and then I can pull out this two summation is the same measure. I can put it out, right? pxy here, and then it will be like just pxy. I have now log px given y minus log px, right? So I can write it as like px given y, log px given y over px, right? So this is the same as that one. So now I can use the, probably this is a recap. I guess I quickly show about this also last time. So then this is, then this will be like, I can use base rule here. Px given y is like pxy over px py, right? So, and then of course this is symmetric. Then I remember this is ixy, right? So look at this form, this is symmetric. We expect like this would be also equal to pyx, iyx. And of course, we can also write it using base rule. I have pxy over py is, I get px given y, right? So I can have pxy over px will get me, this part will get me py given x, right? So therefore this guy is also equal to xy pxy log py given x py, that's basically hy minus hy given x. So also like, you can see why ixy, whenever like ixy is equal to 0, or like when you have like x and y are independent, then ixy will be equal to 0. So when x and y are independent, I have pxy is equal to px times py. So therefore, I will just always have like log 1 here. So I will have ixy equal to 0. And of course, you can do the same thing like for xy given z here. So this guy is a x given z minus x given y z, right? And yeah, I guess I did it before. Like I'm not sure I want to repeat that. So you can do exactly the same. Then maybe I just write it out. This one will be basically equal to summation over x, y, and z, p, x, y, and z log p, x, y given z, p, x given z, p, y given z, something like that. And again, if you read this, immediately you see that if I have x and y, conditionally independent given z, then I have the numerator and the denominator the same. So therefore, like ixy given z is equal to 0. And also this summation form, like let me actually I don't even yeah. Let me also easy to prove something I call it chain rule. That's very, very useful. So something like if I have a joint entropy, so let's say h, x, y, z here. This, of course, this turnout will be like, actually, I may not even need the summation form here, but I can just write it using expectation, maybe like it get me a little bit shorthand notation. It's log p, x, y, z, right? And that I can write it as a minus log px, and then I py given x, and pc given xy. So this is just base rule. So be careful, like this always hold. Like if you have like a joint distribution x, y, z, I can always say like, okay, I want to know what's the probability of x. Now, given probability of x, what is the probability of y? Now, given probability of x and y, what's the probability of z? So I multiply all of them together, I will have this is the joint probability px, y, z. So then this, of course, I can rewrite as a my expectation log px, right? Okay, that's I'm stopping myself here. I want to write in cap actually. Py given x, pc given xy here. So then I have minus expectation log px, right? My plus expectation minus log py given x plus expectation minus log p, I'm missing a p here, pz given xy. So this guy will be just hx, right? And this guy will be hy given x, and this guy of hz given xy. So this is very important. Basically, you will use it all the time. Basically, the amount of information, the joint entropy of like x, y, and z will be, okay, what's the information of x? Now, if I know x, what's the remaining information for y? And now I know both x and y, what's the remaining information of z? So, and I also can have like a chain rule like that, even given a condition. So maybe I have x, y, and z given w here. And you can do the same thing. That one, the conditional joint entropy would be just hx given z. Oh, not z, sorry, w. So I have like joint the entropy of x, y, and z given w will be like, given w was x left behind, and then like given was w and x was y left behind, plus given x, y, and w was z left behind. So that's the chain rule. And I guess like this is a good time to show you that Venn diagram again. So I guess I showed you last time. So this is help you remember stuff. I guess so I have yeah, actually I probably should use better different colors better, but have this one is hy. This one is hx. And then the entire thing here is a h x y. By the way, I guess like we argue like a couple of times, like for example, the amount of information, like we just earlier we argue like hx given y using this discriminant source here. We argue that like or like let's go back even just hx here when you have a px here. We argue that like, okay, if I am going to compress this source here, I need nhx bits to count all the typical sequences. If I label all the typical sequences, therefore like per sample, I need hx bits. But by the way, like this argument is not complete. You see like I guess at the beginning I did warn you like early, but I didn't warn you again like today. It's like my argument was not complete because I'm only saying that like there's exists of approach, right? Because I have an approach now. I'm able to compress this source with hx bits, right? So what it means is like I actually set up a lower bound, right? So it's the lower bound. So I think it's the upper bound, right? Because for this source here, the amount of information has to be less than equal to hx, right? Because I'm able to compress that into just hx bits, right? But I don't have but there's no promise that there's no other approaches. Maybe I can compress it more, right? So if like this has a source, maybe there's some very weird approach. Maybe I can devise some very weird approach that I can able to compress this source less than hx bits. And still I will be able to recover this source losslessly. So if that's the case, then the amount of information, like it'll be less than hx bits, but it may not be equal to hx bits, right? So I give the arguments is actually I just gave the upper bound, but I didn't really show that it has to be equal to hxx because I didn't show that like you cannot compress more. So okay, I think like I was thinking to go into this, like, but it seems a little bit quiet. I'm not sure. Like I should go into that one now, and how about actually I do some exercise for you guys first, like maybe oh, by the way, like you see the homework assignment, right? So you please know that like will be due this Friday, this weekend, and so let me just make up some numerical problem, then I just make sure you guys so. So let's say like if I have, let me just randomly make up something. I have two fair dice. So I have dice, outcome is x, let's say. So x can be like 1, 2, 3, 4, 5, 6, right? And I have dice to like also like maybe 1, 2, 3, 4, 5, 6. So can you guys try to compare, let's say, ix, y given, well, this is probably like z, where z is equal to x plus y. I guess this is what Q6 or something. So I guess let's break like now. And at the same time, maybe you guys, then it's not really a break, but anyway, yeah, but I guess like that's probably like it's a good use of break time. So can you try to solve this? Like so the question is like simple, right? So setup is simple, right? So I have x and y axis is just a two outcome of two dice, or like same dice, but I throw it twice, and then so now z is basically the sum of these two outcomes here. So given z, so what's the mutual information between x and y? Can you try to solve that? So I guess I'll give you 10, 15 minutes or 10 minutes or something. Like we'll be, let's say, back like 4:40. So are you guys still here? Like let me yes. So but the problem is very, very clear, right? So but I just want you just get a little bit more familiar with the concept, and maybe then I will move on to this, let's say, like afterward. Yeah. Yes, X is independent of Y. So this is two independent dies, like you fold it 2 times. Yes, but you need to continue to try to yes, you want to compare hx given z also. You guys are right, like hx given yc is equal to 0. It's a bit tedious, I guess, but it's not too bad. Like I think it shouldn't be too bad. Yes, but yeah, you guys want to end up with numerical values, basically. So this is like the mutual information, just like entropies will have your unit bits, basically. So at the end of the day, you should get like what's the number of bits, basically, like 3.12 or 4.15 or whatever. I don't know. I haven't computed it yet, so I don't know, but Okay, let's come back to this question and so how far are you guys? Like, are you working on that? Like, stuck or like So a couple of you like realize that okay, this is equal to hx given z minus hx given y z, right? And I guess I also a couple of you realize that given y and z, like x is long, right? Because I simply have like x is equal to z minus y, right? So therefore, like this one is 0. So therefore, like this is actually equal to hx given z, right? So this is like the starting point, maybe. So then like if I have hx given z, you can compare multiple way. I guess let's see what I can do. What's the easiest ways? Let's see. I can consider, for example, hx z minus hz. So this is equal to hz minus hz. So so and hxz I can write, for example, as hz given x plus hx, something like that. Let's see, minus hz. I'm just thinking whether I will make it easier. It may or may not. I'm not 100% sure, honestly. But so this one, hz given x is x plus y given, because z is equal to x plus y, right? Given x, right? Plus hx minus hz here, right? So, and we know that like given x, this is just a constant, right? So given x, so therefore like this is actually just hy given x. So, okay, you all agree with that this step is important. So all of you agree with that? Because now given x, then x is just a constant, right? So remember, like if I have x plus k or something like that, it's just equal to hx, right? If k is a constant. So it doesn't change anything. So now x is given, then x essentially is just a constant. So therefore hx plus y given x is just equal to hy given x. Now because x and y are independent, right? So then this is actually just equal to hy, right? So I will just equal to basically hy plus hx. Maybe I just write it directly here. So it's equal to hy plus hx minus hz. So that would be basically equal to this guy here. hx hy is equal, is simple, like hx and hy is just equal to log 6, right? So this is just log 6 here. hz, so what is hz? Is probably a little bit more tedious. So we probably need to consider all the combination here. So z can be equal to 2 and so on up to 12, I guess. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, something like that. So then we probably need to consider all the combination. So, and there's like 36 different combinations here, right? So for z equal to 2, there's only one cases. That's basically x and y is equal to 1, right? X equal to 1, y equal to 1. And for 3, I think that's 2, where x equal to 1, y equal to 2, and the other way around, x equal to 2, y equal to 1, right? So these two cases here. And for 4, let's say I can have x equal to 2, y equal to 2, and x equal to 3, y equal to 1, and so on, and x equal to 1, y equal to 3. So I guess it's 3. I think it's moving upward, something like that. And this here, also 12, I have only one cases here. This is 2 cases, 3 cases, 4 cases, I think, like probably 5, I think it's 6, something like that. Probably it should add up to 16, I think. If it add up to 16, I think it's right. Yeah, I think it does. So that's not 16, added up to 36, right? So therefore, like H0 will be what? Will be something like, let me just put some space here. Hz is equal to, I have this 1/36, log 1/36. That's -1. Maybe I just write 36 is easier. Or I can put a minus sign here, but okay, let's do it like that. So I guess no confusion here. And then minus, this is 18, I think, log 18, right? And so on. Like, actually, I have two of them. Maybe I write 2 here. I have 2 of this case at 1, 2 of case here is a 18 here. I put minus 2, 36 log 3/36, that's 12. And then 2, 18. I took care of this one now. This 2 is a log 4/36. And then I 36 log 5/36 minus 1/36. Oh yeah, sorry, I make mistake here. This is 3/36 is 12. I have 2 of them. And then this is a 9. I have 2 of them. So I'm not sure, like, you guys can check the number. And then I have 5/36. I have 2 over 2 of this 5/36. And then finally I have 1 of this 6. Or something like that. So I'm not sure, like, what's the values. Yeah, if you oops. Okay, okay. So let me repeat again. So let me repeat again. Okay, let me get some more space and repeat again. So let me start with a new space. So we have like maybe I write it here. Like I have like x and y and z, right? X, y are just dice, like they're independent. I have x, y independent, and then z is equal to x plus y here. And that's x and y can just take 6 value, right? 1 to 6 here. So the question is like, what is like I, x, y given z, right? So we start from there, like I, x, y given z is equal to h, x given z minus h, x given y, z there. Now, given y and z, of course, I know x, right? So this is gone, this is just equal to 0. So it's just considered this guy here. So hx given z is equal to, so think of like x given z plus hz is equal to hxz, right? So, right? So you have knowing information c, and then given information c, the remaining x here, when you add these two together, it should be the total information x and z, right? So therefore, hx given z is equal to hx z minus hz, right? So then I just do this same kind of algebra again. I can expand it in another way. So c plus hx given z. So I do all this just because I have some intuition like this is kind of like painful to, actually I can solve this directly, but it seems to me it's a little bit more painful. Like if I try to solve this directly, it will be like equal to sum over pc log px given z. Actually, it may not be actually that bad. I can do it this way also, like it's equal to minus log pz sum over p. Okay, actually, this is wrong. Equal to this way, x given z, small z. So given small c, that's a distribution for x here. For example, like as I show, like as I illustrated in the previous slides here, z can take cases like x and y, let's say, for different combination of x, y, and y, I got z, right? For z, I can have like 2, 3, 4, 5. I cannot have c equal to 1, right? Because my x and y, the minimum value is just 1. So the minimum z has to be start from 2, 6, 7, 8, 9, 10, 11, 12. So the maximum for z is 12. So yeah, that's the probability basically, the probability of each of these guys. So then what's h? So this is a little bit painful to, but it's doable. X given small c. So now if you think of that, it would be like for each of these cases, for example, z equal to 2, then what is the possible x here? Actually, x given z equal to 2, for example, what's that value? Yes. Oh, no. Actually, there's only one cases, but it's equal to 0, right? So do some counting, yes. So do some counting here. Like for z here, like you only have one case, like x can only be 1, right? You cannot have anything else. So therefore it's deterministic. So x is deterministic. So therefore like h is given z equal to 2 is equal to 0. Now I can do each of the cases. X given z equal to 3 here. So x can get value 1 or 2, right? So x can take 1 or 2. If x take 1, then y has to be 2, right? If x take 2, y has to be 1. So, but it can take either of these values. And the probability to either of them will be equal. So therefore, like so what's that? So then it will be just 1, right? Because it should only have 2 outcomes, and 2 outcomes have the same probabilities, or both of them equal to 1/2. So therefore, it will be just equal to 1. So for this case here, when c equal to 4, hx given z equal to 4, my y can take 1, 2, 3 different values, right? So therefore, like it will be just equal to, and again, like they will be uniform. Like all 3 cases can will have equal probability. So therefore, like it will be just equal to log 3 here. You agree with that? So you see the pattern here, right? So therefore, like I can continue to do that. Like x given z equal to 5. So my x can take like 1, 2, 3, 4, right? So therefore, like that would be log 4 or like 2 bits here. Hx equals c equal to 6. Honestly, I'm not 100% sure. But let me continue to see, like if I can take 1, 2, 3, 4, 5. Yeah, I can take 1, 2, 3, 4, 5, right? So yeah, then it should be log 5, I believe, right? And then hx given z equal to 7 here. X can be 1, 2, 3, 4, 5, 6. Then I can have like log 6 here, right? Now then when I go up, it gets tricky. Like if given z equal to a, what's the value like x can be? What is the hx given z equal to a? Yes, the value can only get from 2 to 6. And this, again, like, it will be uniform. I only have 5 cases. Then I'm going back to this case again. I look at, I only have log 5 of them, right? So it's actually the same as I when c equal to 6, the same case as for c equal to 6. Actually, c equal to 8 and c equal to 6 is actually the same case. Here, like you can only take values, say 1, 2, 3, 4, 5. And here you can only take value 2, 3, 4, 5, 6. So again, at both of these two cases, you can only take 5 different values. So then I can continue to do that. Like hx z equal to 9 is log 4 here. X given z equal to 10 is log 3 here. And hx z equal to 11 is log 2 here, and so on. Then I have hx equal to 12 is just equal to 0. So then probability for each of these guys, as how long I showed it earlier. So the probability would be like, for 2, it would be 1/36 here. This is like 2/36 here. This is 3/36 here. That's 4/36 here. There's 5/36 here. This is 6/36 here. There's 5/36 here. So then the total hx given z will be just weigh the sum of this. So it will be 1/36 times 0 plus, maybe I use a different guy, 2/36 times 1 plus 3/36 times log 3, and so on and so forth. And then the final values, I'm not 100% sure what's the final value, honestly. Let's see. So anyone got the values there? I got 1.89 actually. I don't know anyone's got another number 1.895. So, but I guess the numerical value is not important, but the important part is that you understand what's going on here, basically. Yeah. So, do you guys have anything not clear here? So, maybe okay, maybe I continue on if I don't do that. Like, so this is like one way I do this. So this is of course different from like what I did earlier, because I was thinking like computing this may be a little bit tedious, but it turns out maybe it's about the same. So earlier what I did is say, okay, let me convert to something. Maybe HZ is easier to compute, so I'm good with that. So I try to make up something HZ instead of trying to compute this guy. So I have like HX given HXZ minus HZ here. And HXZ is equal to HZ plus HX given Z. And then okay, let me rewrite this. And then HX given Z is equal to, wait, is that, wait, that's not what I want. That's, I'm writing the same thing as I earlier. So I can write as like HX plus HZ given X, right? Now, but Z is equal to X plus Y. So this is a HX, I just copy HX again. It's HX plus Y given X minus HZ. Then again, like given X here, meaning that X is just a constant. So now if you consider the entropy of something at the constant is just doesn't add any information. So this is just equal to HY given X here. And then you have like X and Y are independent. So I have HY given X is just equal to HX equal to HY. So, okay, are you guys okay with these two steps here? So this is very common when people, yeah. So I have HY, remember like HY is equal to HY given X plus IXY. So sometimes if you just get started, like probably the Venn diagram will help. So here like is IXY here. So this here is a HX given Y. Just this thing here. So therefore like this whole thing here, HX, yes?
I didn't understand how we got from HY given X to HY, only that part on the left. The last two lines.
This line or this line? These two lines?
Yeah, these.
For this line here, like, so given X here, now X will be like a constant, right? When you know X, then X is just a constant, right? So then when you say like HX plus a constant, it doesn't do, I mean, it would be just equal to HX, right? You shift the X, the variables like by some constant, it won't actually change the entropy, right? It won't change the amount of information. So therefore, like these two will be the same. So
I'm actually interested in the last lines. I mean, HY given X, then
this
H.
line?
Yeah.
Oh, okay, I haven't finished. That's HC here. Minus HC here. So this is just X and Y independent. So I have like HY given X is equal to HY.
Got it. Thank you.
Yeah. So I'm writing this here just in case if you don't recall like earlier. So because you have also HY is equal to HY given X plus IXY here. So when you have independent, then IXY will be gone, right? It's equal to 0. So also like if you think of that, it's very reasonable, right? When you have X and Y independent, so then like the amount of information knowing X doesn't help, right? So therefore it should be just the same. I mean, HY given X should be just the same as HY. Because you have this additional X that is totally irrelevant, it won't reduce the amount of information for the remaining Y there. So therefore it's still equal to the original HY. So so that's why what we have is I was thinking, okay, this is probably easier to compute. I guess, yeah, it should be, because hxhy is obvious, it's just log 6 here, right? So both of them log 6. I have 2 log 6 here, minus this is a hc here. So we just need to figure out what's hz. So here earlier I say this is equal to 1.895. Maybe I can double check whether the value matches. So I have this is equal to, I don't know what's that, but I have log c here will be just this whole thing. I'm trying to find the entropy for this thing here. So this will be something like 1 over 36 log 1 over 36, oops, minus 2 over 36 log 2 over 36, and minus 3 over 36 log 3 over 36, and so on and so forth, very long, yes. Okay, yes. And let me double check also. Let's say, so C here, so then for that, I can compute HZ here. Maybe you guys can try to compute that also, like if HZ here. So HZ here, therefore, will be, let's see, I have 136. Yeah, I think it's correct. So I'm happy about that. So this is like, if I compute this one here, it should be equal to, yeah, this is equal to 3.27 something if you try to compute the HZ there. If you subtract these two guys, you should get the same values, 1.895. So any questions here? So maybe. So maybe actually, that's one thing, like logistic thing. I guess I promise that we need to get this presentation order as well. So, but so I show you some of this calculation I just did earlier. So, the Q here is the probability of this is probability of Z basically. Q is a probability of Z here. So it's you see like it's 1 over 36 and then 2 over 36 and so on and so forth. Then I have log Q, a Q log Q, sum over together. That would be the entropy of Z here. I'm missing a minus sign, so minus minus. I have a plus here. Then this 2 times log 6 here minus this guy will be the this 2 times log 6 is like the entropy of X plus entropy of Y. So this is, maybe I just write like this, make it clear. So, and this one is the entropy of Z here. So, So this is probability of C, this is just computed entropy of C. So therefore this guy minus that is equal to 1.895 bits. So hopefully you guys don't have any questions for this problem. So okay, this is of course this is not yet. I said I'm going to do a lottery, so I'm doing it now. So of course this is not dramatic. I will just hit shift enter, then it will compute the result. So but ignore this one now. So so that's the outcome now. So I will just stay with this guy. So it'll be the schedule like for you guys. The earliest presenters here like will be like in 14th, and then 22nd, 21st, and 28th, and then we have last two will be like in November. So I'll post the kind of schedule also like on the website. So any questions, concerns? So I will move on to my question earlier then. So let's see, I need to recapture the so coming back from, it's also an exercise, I would say, because let me see. Of using this like entropy and so on. As I said like earlier, that when we try to argue like the definition of hx and hx given y, let's say, so we say, okay, we look at a discrete memory source and we devise a scheme that like we are able to compress the source with like hx bits per sample. So, but I just mentioned that there's a logic hole there because at that time we said, okay, therefore the amount of information from this source will be, whenever the distribution here is px, then the amount of information for this source will be hx. But then we only show that we have one scheme that basically we can compress the source like with hx bits, right? So essentially we are saying we are actually only giving upper bound. Right? The argument earlier is basically saying, okay, the information content is actually less than equal to hx, right? So we didn't actually show the lower bound there. We didn't show that because at that time we don't have enough tools in our toolbox to show that. But with everything we discussed so far, like with the entropy and conditional entropies and so on and so forth, now we can also show that this is bigger than equal to hx. So therefore we complete the entire argument. So therefore like the amount of information in px is indeed is equal to hx. And also like when I have a joint source, let's say px given y there, and if I only consider x and know that what is y there, then indeed the amount of information there is like hx given y. So because I earlier also like by the same argument, we also only show that one scheme we can reach for this conditional case, we can compress the source with hx given y bits, right? So we also actually only show the upper bound is hx given y. But we really need to show that like the actual amount of information contents is really also bigger than equal to hx given y. So I guess I can show either of them. Like maybe I will show this one. Maybe I will leave this like as a homework like later on, or exercise. I don't know, even midterm. I don't know. But what I mean is I will show this here because this probably a little bit more tiny, need to be more involved, about the same. But once you know one of them, is easy to know how you can show the other one. So the tool we use is actually introduced by exactly I mentioned earlier, Huffman's teacher, like Fano's. It is something known as the Fano's inequality. So the Fano's inequality goes as follows. Let's consider this case here. Let's consider this case. So I have this discrete memory source like pxy here. Then I have like px, I have some sequence x coming in. I have y coming out also. Then at the encoder, I'm using this x and y, right? Taking advantage of x and y. And now I have, let's say I consider a sequence of them. I compress that into just a variable c here. And at the decoder, I decode that. And also I use the sign information y again. I recover like x and hat. So assume that like I'm really able to recover that losslessly. So therefore like probability x n not equal to probability x n hat should goes to 0. So Fano like basically introduced an inequality saying that if I have this, let's say if this is true, then I will have h c given xn and yn. Wait, let's see, make sure. Oh, okay, I try. Should be this one. Sorry about that. hxn given c and yn should goes to 0, or more kind of like more precisely, I can say something that like for any epsilon, let's say for any epsilon bigger than 0, I can always find n, exist some n, that n probably is pretty long, very long, that xn cyn will be less than epsilon. So just look at this Fano's inequality. It's actually very lateral, right? If you think of that, because if you don't have any error here, so here is saying that like, okay, I'm lossless now. So if I'm lossless, given c and yn at the decoder here, I can recover xn, right? Xn hat, right? So if I don't have any error, then of course given xn hat, xn will be just the same, right? So therefore xn given xn hat will be just equal to 0, right? Oh, actually, I need to put 1 over n here also. Okay, but anyway, like the idea is the same. So
can you repeat the
yes,
three equations on the left again?
oh, I cannot really hear you. So can you go nearer to the mic again?
Can you explain the 3 equations?
Oops. I have my other computer trying to record, but then because otherwise this desktop, it seems like it will get too hot or something like after a while, but it seems like the other one hang and like stop recording like sometimes, I don't know when. Yeah, so I may lost some of the recording, I don't know. Yeah, I try to make it up, let's see. So what's an MC? Use a Mac. Oh, okay. I have a Mac, but I don't like it. I prefer to use Linux. Yeah. So yeah. Actually, this is the first time I don't know like why. So yeah, probably I opened too many stuffs for this other thing. But so anyway, let me come back to this guy here. So here, this is some kind of a calculus kind of argument here. When I just write like this, it's going to 0. So how fast you're going to 0 is not clear, right? And how, in what way I'm going to 0 is not clear, right? So here, I just try to make it precise. It's basically saying that like, okay, you can pick whatever epsilon, any epsilon you want, like let's say 0.1 or 0.01 or anything. But I can make it very small. So if you don't want 001 or 00, like 10 to minus 100 or something. But the smaller the epsilon is, like probably I will need a larger n, but it doesn't matter. So I will always able to find an n, that n would be pretty big. If, for example, if you pick epsilon is 10 to the minus 100, then I will have n maybe like it's like 10 to the 100 or whatever, such that like I have this hxn cyn over n will be less than epsilon. So this n looks a little bit kind of like, I don't know, n is the number of samples I draw from this source here. So I have this source here. I'm drawing this source a sequence, right, of length n. So if you want a smaller epsilon, I need to draw a longer sequence. So you can think of like, for this encoder, I will draw a sequence of like maybe 100,000 before I encode. So this is pretty weird kind of encoding, right? So you draw a really, really long sequence and then you compress that. If you draw longer the sequence, you can have your compression like performance will be higher. You can compress more, but the complexity will increase exponentially as well. So therefore, like, this is all kind of theoretical. In practice, like, no one actually do that. But of course, like, information theory is about theory, right? So, but that, of course, a theory is important also. Like, give you some kind of insight. So yeah, n is like the length of that sequence that you draw from the source. And so is that clear what I have here? So I'm then like, I'm arguing like this is very obvious, right? So I have this over n because like, if you think of like without this over n would be like pretty crazy. Like this must be increasing indefinitely, right? Because if you have a longer sequence, of course, like the entropy will be higher. But if you per sample, like if you over n, that one will get smaller and smaller and smaller if you draw the sequence to be longer and longer and longer. And also like if I let me repeat this one if like if someone missed it like earlier. So this itself is very reasonable because this I have this one this expression assuming that my probability of error is also approaching 0 as well. So it means that like I will have the decoded sequence will be the probability that like is different from the original sequence will be equal to 0. Or like you can say like this can be arbitrarily small. So if like this will be identical in this guy, so given C and Yn here, now of course I can recover Xn hat, right? And given Xn hat, then of course if I don't have any error, then Hxn given Xn hat would be equal to 0, right? So therefore like this expression is that this Fano inequality is very obvious actually. There's nothing spectacular or like nothing suspicious about that. So let me let's see. I'm thinking like whether I want to show this Fano inequality first or like show that maybe I will show the lower bound first. Then I will show the Fano's inequality. So let's show the lower bound first. So what I mean by lower bound is that, like as I mentioned earlier, we have a scheme that we can compress this source like with hx bits per sample, right? So now I want to argue that like I cannot compress more than that. Like if I compress more than that, then my probability errors will always be non-zero. Or if I do it a flip way, I can argue that like when the probability of error is equal to 0, then if I look at the entropy of this guy here, this one has to be bigger than equal to hx given y. So what I want to show is like hc here per sample. So because like this hc here is like if I look at hc, it's like the amount of information I got compressed that sequence of length n, right? Then per sample, say I'm compressing like hc over n, so many bits per sample, right? So I'm arguing that if I don't have any error, if this whole, then this has to be bigger than or equal to hx given y. So is that clear? So that's what we are trying to show here. And I'm going to use this Fano inequality. And again, I'm going to, okay, I'm delaying the proof for this guy, but just a moment later. But let's assume this is true first, get over with this proof, and then I will come back this Fano inequality. So we want to show this, and we want to actually, okay, I want to change this a little bit to a problem like this: hc plus epsilon over n is bigger than or equal to hx given y. I want to show this instead, and epsilon can be arbitrary small. So since epsilon arbitrary small, so these two are equivalent, right? So this I can set epsilon and whatever small values, but I will show this instead. So now starting from here, immediately we can use okay, actually the first step I'm going to do something like that. I will say hc plus epsilon is bigger than or equal to hc given yn plus epsilon. So this doesn't matter, right? Because this is basically, if I have a conditioning, I always reduce this entropy, right? This is always true. And then I can say this is bigger than or equal to 1 over n hc given yn plus 1 over n, okay, 1 over n put outside, plus hxn given cyn here. So this is exactly, okay, this is by Fano, right? Because we have Fano just saying that, like, okay, I can, as long as I find a big enough n, I can always find there's hxn given cyn would be less than arbitrary epsilon. I can pick whatever epsilon would be smaller than that. So it would be, so I can replace epsilon by this guy. So it's still, this guy will be bigger than or equal to this guy here. So you guys are good with that. So then I think that I can combine these two terms together, right? So this will be just equal to 1 over n h c xn given yn, right? So this is just the chain rule here we used earlier. So and then what next? I'm going to split it in other way. So we expand, we will do this reverse chain rule. So, but I'm going to expand in the other way. So it's equal to 1 over n h xn given yn plus h c given xn yn, right? So I'm just doing the chain rule, but in the other way, right? I just expand this, right, into xn given yn, then like c given xn and yn. Now, if you look at the decoder here, actually look at the encoder here. Given xn and yn, the encoder is deterministic, right? So therefore, this guy is actually just equal to 0. So I only have xn, yn left. Okay, I'm pretty close to this guy now. So, and then I can use the chain rule again. So this is equal to summation hxi yn, and then y, let me write yi minus 1, I equal to 1 to n. So this is basically expanding one element at a time. So I have this, for example, like if I have n equal to 4, I have like x4, y4, this is equal to x1, y4 plus x2 given y4, x1, right? Plus x3 given y4, x1, x2 plus x4 plus y4, x3, something like that, right? So I'm just doing that. This summation is just doing this. So we are about done actually. So then I have this source here is kind of ID, right? So I have xi is actually given yi, the rest is independent, right? So therefore this is actually just equal to something like that, right? Because given this is you have a conditional independence, so or like you can think of like or Markov chain or whatever. You have x and y, your x0, y1, x0, maybe you pull up a pair at a time x1, y1, x2, y2, x3, y3, and so on. These pairs are depends on each other, but the rest are not kind of like depend on one another, right? So therefore, given y, or actually even you, you can ignore all the rest, right? So therefore, I ignore all the rest, and then of course, all of these have the same distribution. It's like all of them is just hx given y. So therefore, this is just equal to hx given y, right? So I have n of them. I sum n of this hx given y together, and over n again. So therefore, eventually just hx given y. So therefore, we show that. So given Fanos, given if this one is true, then we show that like per sample, the compression has to be bigger than equal to hx given y. Now let's show the Fanos inequality then. So for the Fano, should I start with a new page or maybe let me start with a new one. So for the Fanos, we have something like that where I have like 1 over n. I want to show hxn, cyn. This will go to 0 somehow, right? For some epsilon, any epsilon, I will have basically for sufficiently large n, exists n, such that this thing here is less than, just less than is okay, I guess it doesn't matter. Less than epsilon, let's say, or less than equal to, yeah, it's okay actually. So, okay, let's start with this guy here. So I have this expression here. What I'm going to do is I will introduce a new variable e here. It's just like a error indicator, I will call it. So it will be equal to 1 when there's an error. So when xn is not equal to xn hat, right? And equal to 0 otherwise. And note that like PD is equal to 0, right? Basically. Sorry, I should write PE equal to 1 should be equal to 0, right? Or like close to 0. That's what we assume. Like the probability of error is going to 0. This is what we assume, but we just introduce a new random variable to help us to show this thing here. So then what we are going to do here is I will add, I just rewrite this expression, but I will add a dummy thing, HE given xn, yn, c. So why can I do that? So maybe if you don't remember, I have a setup something like that. I have xn here. There's encoder. There's yn here, right? Then I compress into C. Then I have decoder. I have yn here again, right? And I have xn hat. So anyone is lost or something like so. So the setup is clear. The definition of E is clear. So this is 0 because if I given xn and yn and c, let's say okay, given c here, given c and yn, I have xn hat, right? And E only depend on the xn and xn hat, right? So given xn and xn hat, then I know E exactly, right? So therefore this one will be 0, right? So I just adding a 0 here, it doesn't change anything. So but I add this E here, now I can combine these two terms together, right? So it's equal to 1 over n h E xn given c and yn here. Now I'm going to do this, use the same trick as before. I'm just going to use the chain rule again in the opposite direction, or like expand in for the other variables. So I can write it as a h e given c yn plus h xn given e and c yn, right? And now, first of all, for this guy here, E, because it's either 0 and 1, right? So it's a binary number, binary variable. So therefore what? The it's bounded by what? So HE is bounded by what? So okay, let's I don't know what's this like 7 or I don't know. What's that? Right? What's HE bounded by what? Yeah, that's very good. Yeah. So yeah, this because you're binary, right? So you have only two outcomes. So we know earlier that the upper bound is a log the size of the alphabet, right? So therefore it's bounded by 1 here. So you can put other values, but 1 is sufficient for me, right? So it's bounded by 1. And so I have, for this other term here, then I can write this as like hxn given e cyn. Now I can expand this thing here. Let me continue to choose into two cases, right? Because like the conditional entropy here will be like probably E equal to 1, hxn E equal to 1, cyn plus probability E equal to 0, hxn given E equal to 0, cyn. So okay, maybe this is, I don't know, like get you what do we say, 7, this is 8. So what's the value of this guy here? Any other thought? Yeah, I guess so no one have any other guess? Like So think of like think of like all these variables like here. You have like how this picture is very useful. Like you can always go back to look at this picture, like what you have here. So and what's the meaning for E? So when E is equal to 0, what does that mean? Yes, when no error, then what? So you have C and Yn here, C and Yn here. So you have C and Yn here. Both encoder and decoder are deterministic, right? So you have C here, you have Yn here. Then you also know Xn hat, right? So when you know Cyn is the same as actually it's the same as saying that actually I know Xn hat, right? This is the same as, so when you say given E equal to 0, given C and given Yn, is basically, you can also stack like Cyn is also like knowing Xn hat here, right? So when you know Xn hat, and also you know E equal to 0, yeah, certainly I can write. And I also know E equal to 0, then E equal to 0 saying that like Xn is equal to Xn hat, right? So therefore, what is this again? Yes, so this will be just 0, right? I know Cyn. So if I want to write more clearly, it will be something like that, right? Xn E equal to 0, Cyn is basically equal to Hxn given E equal to 0, Cyn Xn hat. So I can write that because I know C and Yn. This is given, like this is already know. I can put it here. It doesn't change anything. It doesn't matter. But given this guy and given this guy here, then will be equal to 0, right? So or like I can even say one more step is like Xn equal to 0, Cyn Xn hat and then Xn, because I given Xn hat and given this guy is equivalent given Xn. I'm given now Xn, given Hxn, given a bunch of stuff. Xn, of course, this is just equal to 0. So yeah, so therefore, like for this thing here, like we can cross out the entire expression here. I only have this left, so I will just have 1 over n, 1 plus p probably E equal to 1. And this Hxn, and this guy here, I have conditioning a bunch of stuff, but the whole thing is less than equal to Hxn, right? So I can say like this is less than equal to Hxn here, right? And then like Hxn over n, this is like basically it will be just equal to Hx, right? So equal to 1 over n plus probability E equal to 1 times Hx. So by the way, like this guy here, maybe I should elaborate also. Like Hxn here, like is equal to Hx I given xi minus 1, something like that, right? I equal to 1 up to n, right? But then like because all this IID, so I will have like I equal to 1 to n xi here. And for each of these hxi is just equal to hx. So I have n of them, I will have n hx. Yeah. So, and then n hx over n will be just hx here. So therefore, like, I will have just this guy here. So with my probability of error is going to 0. So if like this guy, the probability for this one is equal to 0, like approach 0 here. So then what I left is like just 1 over n, right? So therefore, like this will be less than epsilon as long as n is bigger than epsilon, 1 over epsilon, right? Something like. So therefore, like we are done. So oops, yeah, actually, I just realized I spent all the time here. I covered less stuff than I expected, but I guess that's fine. I guess as long as just let me know if you guys have questions. Like, I think it's reasonable that we don't go very quickly because I agree that like many of these stuffs are new to everyone. So so this is kind of understandable. But we I guess I hopefully like it's clear now, like have all the sufficient argument why like hx is like the amount of information like for that variable x, and then like hx given y is the amount of information of x given y, something like that is clear. And I don't know, maybe I should just stop here. I don't know, maybe I should just stop here. Yeah. Wait, Seth, like you have some question? Oh. Yes, let me repeat that about the presentations again. So I'm expecting you guys let me just share my other share the. So, wait a sec, yeah. So, I think you want to, for the presentation, like we, that would be like, I think like two approaches would be easiest if you don't have like something particular in mind. One is like the textbook by Mackay is like quite entertaining. I think like he even have some video lectures and so on, and you have to especially the book is online, like totally online. I guess if I can just open a particular chapter, I don't know. Yeah, there's a PDF here, but probably it's pretty big. Oh, okay, this is only the figures. But let's see which one is the. Yeah, I don't know where to. I get confused at where's the figures provide. As well as whole book, yeah, this one. Yeah, that's the PDF. Yeah. So Mackay's textbook covered lots of different things, and I guess that you can totally go into a particular chapter and try to just talk about them. And of course, you can go for other textbook as well, but like this one, I think Mackay's textbook is one of the most readable. And set marginalization. for example, they have like some interesting topic. I don't know, not many of them, like what have sex, information acquisition and evolution and so on. So you can pick a chapter and talk about that. And other, so honestly, like Converse textbook is a bit harder to read, but itself is quite interesting as well. But of course, it's not available online. There's Converse and Thomas. It has it's a little bit more mathematically inclined, but it has, for example, we talk about some stock market and like betting and so on, like quite a lot of stuff. Like, and you can totally again, I go into a chapter or session and try to understand that and talk about that. So that's one possible approach. The other one is, as I said, like you can go for a library. Like, do I have a link here? Like, yeah, maybe I don't actually, but you can just wiki probabilistic programming. So there are a bunch, right? So and you can, and many of them have nice tutorials. So you can go for any of these and look for, maybe try to go through some of the tutorial and try to explain those. And for example, like I know Stan, for example, this is like quite popular bugs also, like it's kind of old school, I guess. Bugs and Stan like kind of old school. But I believe still many people use that. And if you want to go for example, like as I mentioned earlier, if you want to go for something like more modern, you can go for Pyro. Let's say like it's based on PyTorch. And also you have libraries based on TensorFlow as well, like for example, Edward and so on. And you can, for example, like Pyro, for example, you have like lots of like example documentation, like you have example like, and you can understand some of this and then maybe try to give a, they have like introduction, like in some, like the earlier part probably is like quite simple, like you have this like just reasonably elementary, for example, like there's some of this map and like maximum likelihood estimation and so on. And of course, you can go to other library. As I said, the boxes would be, no, I guess yeah, it's a little bit old school actually. I don't know, like, but you should be able to find the some of these I mean those tutorials or documentation online. So, and any other questions? Yeah. Less than half an hour, I think, like half an hour, something like so not too short, maybe 20 to 30 minutes, like 20 will be too short, like 25, maybe aim for like something like 25 approximately. Then so, and I want to put up the kind of like an assignment, like so that you can submit your abstract of your presentation. So I guess you probably want to browsing some of this idea early, just I see what you like to talk about. And basically you can talk about any, I would say like you can talk about anything, not we. Actually, even something we mentioned here, like you may still talk about if you think like, I didn't explain like really clearly, like you think that, okay, the instructor said this, but then I thought it's actually like that, and realized, okay, actually he meant that, and then I want to clarify later. I guess it's fine as well. And as always, in the past, I'm going to grade you like based on the peer review. So I have you guys to kind of review each other as well. So of course, I give a little bit incentive for you guys to do the review, like to make the effort to do the review. Basically, a part of your presentation score is based on the review yourself to the others. Yeah, and then like, yeah, so in the past, I always did that. Like once I have your peer reviews, my job is very easy. And in the sense I almost always based on your final score for the presentation part is based on the peer review. I have my opinion, but my opinion pretty light there. So sometimes I think, oh yeah, this is a bad presentation. But then I saw the review, okay, everyone is positive, then I changed my mind. So you still get a good grade. So therefore, in the sense that you want to target this to your peer instead of like targeting to me, like something like you're thinking, okay, if for example, like when sometimes I'm not clear myself also, like especially if I don't have much feedback, immediate feedback from you guys, sometimes I don't really not sure whether I explained clearly or not. Maybe sometimes I didn't, and then like maybe you want to elaborate parts of that, like, and then like you think like many others will be useful, like for many others, and they will appreciate that. Then I guess that's okay as well. Yeah, but yeah, but of course, you cannot just repeat everything I just said. Like for example, like repeat all the materials that we cover in class, then do it one more time, then probably it's not very good presentation. And unless you really do an excellent job, like elaborating some unknown idea that that was not discussed earlier, and everyone think that is, well, yeah, that's cool. But I guess my experience is like the audience are always quite fair. Like they give a pretty fair judgment. So when you say something like, this already discussed in class, most people like will consider this is not if you do something like too trivial, that like my experience say the audience will kind of like discount for that as well. So, but I mean, I'm very open like what you guys are going to discuss. But of course, is within the context I discuss in class, right? So maybe something related using some information and so on, and or like relating to trying to use a programming to solve some these probabilistic problems and so on. Yeah. So I guess any other questions or comments, and if not, I'm going to shut it down. But I guess before doing that, I probably should try to save the chat history. Yeah. So I will. Okay. Okay. I guess that's the end, and I'll see you guys next Wednesday then. Okay.
Thank you.
Thanks.